Welcome. In this session, we're going to explore the geometry of KKT points for a problem that has a single equality constraint. We looked at equality constraints in previous sessions. Now we're going to take the understanding of these most recent sessions and we'll apply it to a new problem. So suppose that we have this objective function, and what we have is a single equality constraint. So we'll write this constraint. We've explored this in previous sessions. Is we use the constraint 1 minus 1 times w plus 3, and now we're going to say that must be equal to 0. And when we did our geometrical solution, what we found was that our W star for that was 2.4 and minus 0.6. And what we found was that we have to use mu because it's an equality multiplier. So that was minus 4.8. Now, why is that Lagrange multiplier negative? Well, we were never promised in the KKT conditions that the Lagrange multiplier for an equality constraint had to be non-negative. And as we can see, it's quite possible for it to be negative. So what's going on here? Well, if I draw the contours for this problem, they'll look something like this, right? And then if I draw this constraint out, what I see is that it will look something like this. Okay? So what is the perpendicular to this constraint line? Well, that turns out to have two answers. I could say that this is the perpendicular, or I could say that that is the perpendicular. And geometrically, because this is a line in 2 space, each one of these is a perfectly reasonable and possible perpendicular. Well, what does that look like algebraically? Well, we could rewrite this as 2 simultaneous inequalities. So we could write this as, we could say that this is some one form times our vector argument minus some constraint scalar is less than or equal to 0. And that would be one of these two. But if I multiply this by minus 1, I could equally, if I multiply the constraint by minus 1, I still get the constraint. Here's what I mean. This constraint is an equality constraint, meaning it has to equal 0. If I multiply both sides of an equality by minus 1, it's still equal to 0. So the algebra stays, but the geometry has changed, because if I negate that, that's equivalent to saying that minus that one form times w plus the constraint scalar has to be less than or equal to 0. Now, these conditions will both obtain if and only if w is on that constraint line. For one of these, so if we picked this to be the perpendicular to this constraint line, then its feasible set would be everything over here. And that would mean that that Lagrange multiplier would equal 0 because the unconstrained minimizer would be in its feasible set. If we pick this to be the perpendicular, then the feasible set would be here, and then that constraint would be active. So it turns out that if we write this equality constraint as 2 inequalities, one is going to be inactive, one is going to be active. For the active one, it will have a positive Lagrange multiplier, except in the extremely unlikely case that the unconstrained minimizer is exactly on the constraint line. That's very unlikely. So in general, one of these is going to be inactive, one's going to be inactive. It will have a lambda that is positive, and this numerical effect of a negative multiplier for an equality constraint is a purely numerical effect. So let's take a look at the geometry when we plot this in MATLAB. When I use MATLAB to plot this problem, here's what I get. I get exactly the picture that I drew by hand, which is these lines are the contours of this objective function. This bright line is the equality constraint, and then these are indicating two of the possible normals for this equality constraint. So if we pick this as the feasible, if we pick this as the perpendicular and we describe the equality constraint as an inequality, we'll see that this is the feasible set and the unconstrained minimizer is in the feasible set, and so that constraint would be inactive. If we reverse it, that is, if we simply multiply by -1, then that gives us this as the perpendicular, and now this shaded region is the feasible set. The unconstrained minimizer is not in the feasible set, the constraint is active, and the Lagrange multiplier will be positive, and the solution will be on the boundary point. That is to say, the equality will be satisfied. So what can we summarize out of this entire lecture? Well, from dual feasibility, every Lagrange multiplier is 0 or positive. Complementary slackness says that the Lagrange multiplier is 0 or it isn't. This is basically the law of excluded middle. A Lagrange multiplier that's 0 means that the constraint is inactive. There can be two reasons for this. One is that perhaps that objective function is in the feasible set of the constraint, or perhaps that constraint has been inactivated by another constraint. When the Lagrange multiplier is positive, we're dealing with an active constraint. And we can treat equality constraints conceptually as two inequalities. Of course, computationally, we wouldn't want to do that because it's much too expensive. And for equality constraints, we have primal and dual methods that work very well to solve our problems.